Gabriel, thank you so much for agreeing to come to present at the working group. I know it's very late for you, but thank you for taking your time. Gabriel is a PhD student at McGill University and also a member of the NASA Harvest machine learning team. Today he will be talking about Presto, which is a very lightweight pre-trained foundational model for remote sensing data, mostly agriculture specific focused, but I'm assuming you can use it for any kind of time series applications, and he will talk more about that today. So without wasting any more time, Gabriel, why don't you take it away?
Awesome, thank you. I won't be able to hear you, but feel free to interrupt with questions, and then hopefully there will be plenty of time for questions at the end. I'm Gabi. Nice to meet you all, and I'm going to be talking about Presto, a lightweight pre-trained transformer-based model for remote sensing time series. And this is work that I did with a bunch of other co-authors, Ruben, Ivan, Morali, and then you might know Dave Rolnick and Hannah Kerner from NASA Harvest. Okay, so I'll start with the motivation a little bit. I'm realizing that there are, some of this might be repeated because there's been more and more discourse around foundation models for remote sensing, but I think it's helpful background anyway. In machine learning, and especially in deep learning, for instance, in computer vision, it's now really common to take models that have been pre-trained on large data sets, such as ImageNet, and apply them to a huge variety of different downstream tasks. And it's kind of a surprising thing that you can take a ResNet model that's been trained on classification and find that it works well for T-pose detection, segmentation, bounding box detection, all sorts of different things in relatively different domains. And from a remote sensing perspective, that's really attractive as well, because we're often in a situation where we have many different tasks that we want to gain insight on about the world. And sometimes we have very little data or very little labels with which to train a model to achieve these tasks. And so taking something that's been pre-trained and that has a good internal representation of the world is really attractive. Remote sensing is not computer vision. And so as a remote sensing practitioner making maps on the Harvest team, there are a few things that I would like this model to have that differs from a standard computer vision pre-trained model. The first thing I'd like it to do is let me use whatever sensors and time steps are available and appropriate for a downstream task. To illustrate this a little bit, this is ERA 5 coverage in Maui County in Hawaii, ERA 5 climatology data, and you can see that basically it's incomplete. In some parts of the island, I don't have access to ERA 5 data. But ERA 5, especially for agriculture, climatology data is really useful. So I'd like to be able to use the ERA 5 data if I had, but ignore it if I don't. To kind of illustrate this point a little bit more, this is a table made by Ben Strong, who I believe spoke here a few weeks ago, but he's also working on models for remote sensing through the Earth genome, and he mapped out for a whole host of different tasks which kind of signal is important, from the spectral signal to the temporal signal to the spatial signal. And something that stands out to me is that depending on the task, you need a different combination of these signals. And so it'd be really nice to have a model that can ingest whichever signal is relevant for a specific task. Another thing, this one perhaps is kind of obvious, but if we're going to make the claim that anyone can use it for whatever remote sensing task they have, these models need to work anywhere in the world. And sometimes that's not entirely easy to do. And finally, and this is one that I consider really critical, they need to be small enough for large-scale inference. So the screenshot on the right is from a blog post by Christoph van Schrik from Vito. And Vito is part of the organization that's leading, Vito is the organization leading the World Cereals Project, which is making global agricultural land cover maps. And one of their key considerations when they were selecting an algorithm with which to make these maps was the computational cost of running these models. Because if you're making a prediction over trillions of pixels at global scale, small differences in like inference cost can really add up quickly. So when masked autoencoding is now becoming increasingly popular, so it's possible that some of you have heard of it and already really familiar with it. I'm going to go over the outline anyway because it's a helpful background. But in general, when we have tons of unlabeled data, which is definitely the case for us in remote sensing, it's really useful to have algorithms that can build these representations of the world without any labels. And masked autoencoding is emerging as a really nifty potential solution to this. Maybe emerging, it is now established as a really nice potential solution for this. So the basic idea of masked autoencoding is you take some input and you split it into patches. And these are analogous to tokens in natural language. You then linearly project these patches into an embedding space. And now that they're in this embedding space, we call them tokens, and you randomly remove a bunch of them. You pass whatever you've kept through a transformer-based encoder, and then you fill in the missing tokens with a mask token. And this mask token is just a learned vector that tells the model, there was something here and I took it out. And then you pass the complete token set through a transformer-based decoder to reconstruct the input. And you can train both the encoder and the decoder in this way, but at inference time, whenever you're doing something with your downstream task, you'll only care about the encoder and you'll discard the decoder. So there are now quite a number of applications of masked autoencoding to satellite data, but I think I'd argue that they kind of fail to meet these pre-trained model requirements that I outlined just now. So here I'm going to focus on two, and I'm focusing on these two because I think they're a little bit canonical now within this space. SATME, which first introduced masked autoencoding to satellite data, and ScaleMe. So the first thing that I wanted these models to do is to let me use whatever sensors and time steps are available and appropriate for a downstream task. For both SATME and ScaleMe, but generally for MAE applications to remote sensing data, it's rarely the case. They're very often trained on, at most, data from a single sensor, for instance, Sentinel-2, and on, at most, 3 time steps of data. And that's really not enough to capture, for instance, change over an agricultural season. We'd like them to work anywhere in the world, but a really common pre-training data set for these models is the functional map of the world data set. This plot up here shows the spatial distribution of this data set, where green tiles have many more images and blue tiles have less. And you can kind of see that there's a pretty strong bias in North America and Europe for this data set. So it's a question mark because they're both trained on this geographically biased data set, but they are tested on more diverse data sets. And then finally, the one I described as critical, which is to be small enough for large-scale inference. So at NASA Harvest, we also make agricultural land cover maps, and we have this model in red, which is what we've currently deployed, a tiny LSTM-based model. In green is the Presto model, which I'll introduce in more detail in the next few slides. But the thing to take away is SATME and ScaleMe are the massive orange and blue circles. They're about 1,000 times bigger than Presto, and as a consequence, many thousand times bigger than this currently deployed model. And so what are we missing? Or perhaps phrased differently, what are the opportunities in remote sensing data that can let us train small but still performant models? The first thing is that remote sensing data contains many complementary sensors. Perhaps coming from a background in computer vision, it's natural to only take one sensor, like Sentinel-2, as input to these models. But these are just the sentinels in this image on the left. And in addition to the many complementary satellites, we have loads of derived data products that can be really information dense and really important for downstream tasks. And so these might include the climatology data that I was talking about, year 5, but also, as an example, outputs of other machine learning models. So here on the right is a land cover mask generated by Dynamic World. It's at Sentinel-2 scale, and it's available for any time step for which there's a cloud-free Sentinel-2 pixel. So it's actually really spatially and temporally complete. And so it makes a lot of sense to include these in your models as well, because they're going to be providing tons of information at pre-training time, and if it's available for your downstream task as well. We collect remote sensing data everywhere on Earth, So it's a great opportunity to make a well-sampled representative training data set, pre-training data set. And finally, at the resolution of open remote sensing data, so here I'm talking about the Sentinels, Landsat, MODIS, this kind of thing, large spatial context is a lot less useful. And so you can use much smaller networks. The VIT backbones that are commonly used by these masked auto-encoding models were inspired by computer vision, where you often need to ingest many pixels at once to get a sense that you're looking at a bull or an elephant or something like this. But the dynamic world team, when they were creating their land cover maps using Sentinel-2 data, found that you can get away with a much smaller spatial context at a 10-meter resolution. And as a result, you can get away with a much smaller model. And intuitively, if you have even a 10 by 10 spatial context at a 10-meter resolution, you're already covering hundreds of meters. Okay, and so now I've talked about the opportunity. I'll talk about how we design Presto specifically to fill these gaps or to leverage these opportunities. And so I'll step through this diagram bit by bit. The first thing we do is we use a wide diversity of input sensors at pre-training time. So we're using Sentinel-2, Sentinel-1. We are using the climatology data I talked about. We use the dynamic world land cover maps. We're using elevation, like topography data from SRTM, as well as location metadata for each input. As I mentioned, we're aware that at downstream time, you might not have access to all of these different channels. You might not have access to 12 time steps, or you might not need 12 time steps of data. And so we applied structured masking strategies specifically so that the model can handle these missing channels or time steps. And that's structured masking strategies compared to the random masking strategies commonly used for masked autoencoding models. And finally, we use time series inputs. So we use pixel time series inputs, which are much, much smaller than images. And so you get much smaller inputs compared to the images. And that's one of the big things that allows us to get away with a much smaller model. The structured masking that I described allows Presto to reconstruct entirely missing bands. So I'll talk a little bit about what's going on in this diagram. We took an input, we completely removed the Sentinel-2 RGB data, and then we asked Presto to reconstruct it. And I think there are two takeaways. And so yeah, on the top row is the original input that we removed, and on the bottom are Presto's reconstructions. And there are two things to take away from this table, I think, or from this diagram. The first is that, Presto is able to reconstruct RGB even though it's completely removed. And the second is that I mentioned that Presto was a pixel time series models. And that means that Presto is reconstructing this input pixel by pixel with no spatial information. And we're still seeing spatially very coherent outputs. And so that's kind of nice. It a little bit validates that maybe a large spatial context is a little bit less important at this resolution of data. Yeah, and one final thing is that we specifically selected the training data for global representation and diversity. So we tried to sample from around the world, and we also tried to sample semantically varied tiles, so area where there was many different land cover classes represented as determined by the world cover land cover map. Okay, so here I've talked about Presto and how we designed it. Now I'm going to talk about how we evaluated it and basically how we tried to make sure that it delivered on some of the promises or what we were hoping that it would achieve. So I'll talk a bit about this table, but these are all of the evaluation tasks against which we evaluate Presto. This column now that's highlighted in green is the input shape for all of these different tasks. And it's something I really want to emphasize is that we're evaluating Presto with inputs of very different shapes. The bolded value here is the number of time steps. So we're going from 12 time steps, which is a year of data, to 24 time steps to single time step images. We're covering a whole bunch of different input channels from 3 to 19. And also the input shape varies very significantly from kind of a standard image, 64 by 64 by 3, all the way down to the pixel time series 1 by 1 by 12. We also evaluate Presto on a variety of training set sizes, from very small, 200 training samples, to very large, 45,000 for tree set. And a big variety of task types, ranging from segmentation to classification, where you take a bunch of pixels and you make a single prediction for all of them, to multi-label classification, to regressions. And also we evaluate Presto in a variety of geographies, East Africa, West Africa, South America, Europe, and North America as well. So I won't talk about all of these different tasks. They're all available in the paper, but I'll focus on a few. The overall message is that Presto does pretty well in spite of how different all of these different tasks are. Okay, so I'll focus on 2 tasks that I think are particularly interesting to look at. And the first that I'll look at is the crop harvest task. So this task consists of crop land and crop type classification in 3 different countries, Togo, Brazil, and Kenya. And so for the different countries, we're either doing a specific crop type. In Kenya, it's maize. In Brazil, it's coffee. And in Togo, we're just doing crop versus non-crop classification. And we're comparing Presto to a random forest baseline, but also mosaics, which is an unsupervised algorithm, and TIML, which is a meta-learning algorithm, which for now was the best results that we were getting on the crop harvest data set. So the first thing to note is that Presto is really parameter efficient to adapt to these different data sets. So because TIML was a meta-learning algorithm, the whole model had to be fine-tuned to get strong results on these different tasks. And so that required thousands or tens of thousands of parameters to be tuned. But Presto can be treated just as a feature extractor, and we can just train different simple models on top, in this case, a logistic regression. And since the output features of Presto are only 128 dimensions, you only need to learn 129 parameters in order to adapt Presto to this specific task and get really strong results. The other thing to note from this table is that we can remove data in the form of removing channels or removing time steps and still get strong performance. So first, looking at the table on the left, the bottom 2 rows are the results with Presto. The top row is with a full input, so that's with all of the inputs I described earlier. And the row below is if we remove dynamic world as an input. And that better reflects what all of these other models receive as input as well. And kind of the takeaway is if we look at the mean F1 score across these 3 tasks, the change is negligible, whether we have the full input or without dynamic world. And on the right, so the input for the crop harvest data is a pixel time series, 12 months of data. And so here we measure Presto's performance as we start reducing the number of time steps that we pass to the model. And the dashed lines in orange is TIML and the meta-learning algorithm, and in green is mosaics when they're past the full 12 months. And kind of the takeaway here is that Presto can recover the performance of these models even when it receives many less time steps than the full 12-month time series. Okay, now moving on to the Eurosat dataset. To get these results, we took the Presto encodings, again treating it as a feature extractor, and trained a KNN classifier on the encodings. And this follows what ScaleMay did to evaluate their models on the Eurosat dataset. And the other thing that ScaleMay did that we follow is measure the performance of their models at a variety of input resolutions. So the full input resolution of Eurosat is 64 by 64, and then this is reducing the resolution. So 32 by 32 means we've basically taken every 4 pixels and merged them into a single pixel, so on and so forth. The main story here is that even though, as I mentioned, these other MAE models are significantly larger than Presto, we're performing competitively with them, and even in some cases outperforming them. And of course, it's nice if our model is smaller in terms of parameters, but what we really care about is its computational efficiency. How many flops does it take to make a prediction? And so here we also measure the number of gigaflops required to encode an image and create this encoding that we then pass on to the KNN classifier. And so something that's really interesting is that Presto requires orders of magnitude less flops to encode an image compared to these other models. And so one other thing is that these other models all resize their inputs because there's an optimal size for normal image-based VITs, and performance changes as you deviate from this optimal size. And so even as resolution changes, the number of flops required to encode the image doesn't change. For Presto, we can just pass less pixels through to the model. And so you get big gains in flops without penalizing performance excessively. Something to note, though, is that at the full resolution, you can kind of see we do quite a bit worse than these other models. And I think that that's one of the big weaknesses of Presto, is that without incorporating any spatial context, you definitely lose out some. So it depends on this compute performance trade-off, where exactly you want to land. And yeah, as I've noted now a few times, when we're creating these encodings in the case of Eurosat, we're discarding all spatial information in the images. So the way that we're creating a vector that can be passed to the KNN head is we're encoding each pixel individually, and then getting many encodings, one for each pixel, and then taking the mean and standard deviation of all of these encodings. And that's what we then pass on to the KNN head. Okay, so this is the performance on Presto on benchmark datasets, and I think that that's informative. But what I think is really neat is that we're also actively using and testing Presto in challenging deployed contexts. So we're making maps with Presto. So this is an example is mapping taro in Maui County in Hawaii. It's really hard because it's really hard to get very many labels, but Presto was able to make some nice taro maps for us. Of course, we have very few labels for taro, like less than 100, so it's a little bit harder to quantitatively validate the performance of Presto. We're doing many qualitative evaluations. And so for quantitative evaluations in a deployed context, I'll talk a little bit about the work now that we're doing jointly with the World Serial team. World Serial is a European Space Agency funded project to map agriculture globally. And so there are 2 phases to their project, and they've just wrapped up this first phase where they mapped maize and temporary crops globally. The way that they did this was by designing expert features with remote sensing inputs, feeding those expert features into a CapBoost classifier, and then making predictions with this whole pipeline. Now we're looking at whether Presto is a suitable replacement for these expert features. There are a variety of reasons, but one of the reasons, for instance, is that if you want to map additional crops than maize, you might have very imbalanced data sets. Whereas with cropland, you can go and photo interpret labels so that you have a well-balanced, globally distributed data set. For crop type, that's much harder. And so there might be parts of the world where you have very little data. And so we're interested in whether Presto can generalize spatially and perhaps temporally better than these expert features. However, World Serial already have this very nice system in place to make these predictions, and we don't want to come and tear everything out. We want to work within their system. And that's why we're looking to replace a small component of the system, not the whole thing. And so these are results that we've done jointly with the World Serial team, comparing the World Serial expert features as input to this CapBoost algorithm versus a fine-tuned Presto model. So this is F1 score in a variety of regimes. I'll talk about all of them, but to start with, you'll see that the F1 score for these Presto features is consistently higher than the World Serial expert features. And that's really neat because there's no point during the Presto training where we're explicitly passing agricultural features to it or telling it about agriculture or anything like this. So it's really neat that it's able to perform equivalently and outperform these expert features designed by World Serial. Okay, I'll talk about these 3 evaluation regimes that we were looking at. The first, random, is your standard random train test split, where we took all of the World Serial labels and randomly split them. Oh, and I should also say that this is for crop land classification, which is where we started. So crop, non-crop classification. The spatial results, here we're investigating Presto's ability to generalize spatially. So we defined a number of countries, removed them from the training set, and then evaluated Presto's performance on those countries. And then the temporal, we had data up to 2021 in the labeled data set. So we took 2021 as the evaluation year and only trained on data before 2021. And here is just a map that we made with Presto, comparing it to the expert features. This is a map in Belgium. I should note that, it gives a qualitative validation of the Presto algorithm, but it's not an apples to apples comparison because this specific map was made with some post-processing of the expert features algorithm, including some smoothing, which is why it looks especially coarse compared to Presto. I'll talk a little bit about the spatial generalization because I think it's a little bit interesting. So these were the countries that we decided to hold out. For both models, so for the world serial expert features and for Presto, we compared what was the performance for when those countries were held out to the random split. And so that gives some idea of how much does the performance suffer when Argentina is in the training set versus when it's not. So yeah, it's kind of neat to see that Presto does better in absolute F1 score, but also suffers less of a drop compared to the expert features. Okay, and finally, we've tried to make Presto as easy as possible to access. It's easy to load from a Python package. We have a single file version, so basically a presto.py that you can just take and copy into your other applications if it's something that is useful. The model weights are all stored on Git. A really nice advantage of having a small model is that the weights are only 3 megabytes. And finally, it's possible to fine-tune Presto for the fuel moisture task in 6 minutes on a 2017 MacBook Pro. So it really does run on whatever hardware you might have, which is really nice, at least for exploration. So yeah, please feel free to go and play with it and see whether it's useful for you. So in summary, we introduced Presto, this lightweight, computationally efficient model. It's designed to ingest a wide variety of remote sensing inputs, and it's also performant in a bunch of different regimes. The code for Presto is available at this GitHub link, NASA/Harvest/Presto. All of the experiments we did alongside World Serial are also up on GitHub at this different GitHub link, World Serial/Presto World Serial. And finally, we have a paper on archive. This is a link, but if you just search the title lightweight pre-trained transformers, hopefully you'll find it too. Yep. Are there any questions? I'll stop sharing and go back, but I can start sharing again the slides if that would be helpful for questions. Cool. I have no idea who started raising hands first. So, Viplav, did you get to see?
I can help with that. Thank you.
I think it's Emil first.
Emil, yeah.
No, actually, I think Matthew had a question, but then I guess he took down his hand, so I didn't know if he wanted to go first. Or, he was trying to clap.
He's trying to clap.
All right.
Thank you.
Yeah, really nice presentation, Gabriel. Is there any chance you could pull up I guess one of your first slides where you had the spectral band, the spectral image predictions from Presto?
Yeah, I'm going to just. Sorry, this will be a little bit more noisy, but
yeah, no worries.
I think this.
I guess you showed I guess what the originals were and the reconstructed image. Yeah, yes, yeah. Slide 29. Just out of curiosity, is it me? So if I'm interpreting the slides correctly, though, it does look like the original versus the reconstructed, like I guess the coloring, etc. Am I interpreting it right that the spectral information from the reconstructed might not necessarily match the originals well?
Yeah, that's a good question. So I guess I'll start by saying that we were playing a little bit with the contrast just to try and make the features as visible as possible. But yeah, because we're not thinking about, as I mentioned, we're basically discarding the decoder. From our perspective, the reconstruction is useful as a pre-training signal, but I wouldn't use Presto, like for instance, as a cloud removal algorithm or something like this. So yeah, these are just illustrative. I wouldn't have strong metrics to say how good these reconstructions actually are for some downstream use.
And if I could follow that up with, I guess, one more question, and it's kind of relevant to some of the other, I think your later slides where you showed the, I guess, the results of the classifications, and I guess rather the accuracies of the classifications, I guess, and maybe you could kind of explain a little bit. I'm guessing then that you're not using the reconstructed spectral data for the classifications, or are you? Because again, it seemed like you were getting some really great accuracies with the different comparisons that you showed. And so then I guess just kind of looking at this particular slide, kind of wondering if, you know, maybe it has to do with the differences between the features, you know, in the imagery themselves, and not necessarily the you know, the original spectral values or something. But I would then wonder if you know, where classifications, you know, can be based on spectral values, you know, reflectances, etc. And if if the model isn't able to kind of replicate those spectral patterns, then wouldn't that have downstream impacts on the classification outputs? But maybe I'm understanding the process wrong. Over.
Okay. So just to make sure I'm understanding your question correctly, you're asking, since is Presto using these reconstructions when it's making downstream predictions? Because if it is, the fact that these are like inaccurate would like put the quality of the predictions into doubt. Is that interpreting the question right?
Yes.
Okay, excellent. So to answer the first question, no, Presto is not using these reconstructions at downstream time. So I'll go back to the original MA diagram because it's a bit bigger, but basically the reconstructions are done by this decoder. And the only reason we use them is to provide a learning signal to the model, basically to have some gradient that we can pass to the encoder to improve it. But actually, when we're making predictions, we're only using the output of the encoder. So I suppose you could say that implicitly, the model has learned something about reconstructing the missing inputs, and it is leveraging that information at downstream time, but it's not explicitly using anything like the reconstructions in this slide at downstream time. I hope that answers your question.
Yeah. Thank you so much, Gabriel. And just to say too, I really like, I also like how you've simplified or tried to make it easier for those of us who might not be as in the weeds with the deep learning stuff, kind of explaining, you know, piece by piece. And again, if you're one of Jeff's students, and I see Jeff is on the line, I guess kudos to Jeff as a mentor. And of course, I guess if this is building up to your defending, if I was following everything correctly, then again, I really like your style of kind of walking people through the different steps of what's going on. So thank you, and no further questions from my side.
Thank you.
So if I could just jump in there. In fact, Emil, I haven't met Gabriel before. So we're both in parallel at McGill. And Gabriel, maybe you could talk a little bit about David Rolnick, just to help people get oriented there.
Yeah, for sure. So I'm supervised by Dave Rolnick. He's a professor of computer science at McGill, and also Mila, which is it used to stand for the Montreal Institute of Learning Algorithms. It now is just a noun in itself, and it's a collection of machine learning professors. Basically, many of the folks working on machine learning within Montreal are part of this additional organization. David's lab is focused on climate change mitigation and adaptation strategies in general, and specifically on how machine learning can be a useful tool within these strategies. So I mentioned my focus is remote sensing, and Biplov mentioned as well. I look specifically at agricultural land cover mapping, but I also think deeply from a machine learning perspective about how we can improve these algorithms, how we can do better by remote sensing with our machine learning algorithms.
Awesome. Thank you. Thank you so much. I have a question, but I just wanted to start by saying it was great giving some background on SAT-MA, Scale-MA, transformers, what are the gaps in there, and how Presto was designed, keeping all those in mind. So I'm interested in knowing more about what are the downstream tasks that people have been doing using Presto, because one of the issue I guess we ran into using a Prithvi model, which is another HLS based foundational model, especially version 1 it was mostly trained on the US. So if we want to use that outside of the US, that wasn't a major issue. But with Presto, it looks like you have been training this all over the earth, and you have like different downstream application that you presented here. But other than that, like how people are using it, and especially in production environment, and this I guess links to the clay foundational model, like how they are doing it when you want to fine tune, and they have this UI where you can just go and add more labels, and the model will fine-tune itself on the fly. So I'm trying to think on that line, if someone wants to use this for a downstream application in a production setting, having this UI UX interface so that user could come back, add more labels. How does that mechanism work? Like, do we need to go back and do the encoder again, or it's just working on the freezed weight from the encoder and just working on the decoder?
Okay. So in terms of like generally the UI for using Presto, the UI is the code right now. It's to take, like, the most accessible thing is to take this single file Presto that I described and playing with that a little bit. Okay, and then in terms of like how Presto can be fine-tuned or adapted to different tasks, I think that there are two answers here. The first is to just use the embeddings, and I think that this is becoming increasingly popular, like with folks like the Clay Foundation model and also the Earth Genome Project and things like this. And it's actually something that we have been discussing over at Harvest about the feasibility of putting some of the Presto encodings just on Google Earth Engine, for instance, so that lots of folks can access it. The main reason we haven't so far is because, well, firstly, because it's not trivial to do that, but secondly, because certainly with the work we're seeing with World Serial, there's a lot of value if you have sufficient data of fine-tuning the model. And so with World Serial, those results I showed were basically first fine-tuning the model on World Serial's data and then training the CapBoost classifier. And we also have results when we just take the normal Presto model, and the results are still like good, but they're a little bit less good. And so I hope the main use I see right now of folks using Presto is folks who are able to fine-tune it, take the model, fine-tune it, and then use it for their own tasks. It's other researchers or programmers. But yeah, we are also thinking deeply about how it can be made more accessible, such as by making the encodings more widely accessible. I hope that answers your question. I know it's like sort of a non-answer, but it's like a work in progress for us is the answer, I guess.
Okay, thank you. Michael?
Hi, Gabi, great to see you again. Thanks so much. I spoke with Gabi a couple of months ago for some of my PhD research looking at crop phenology timing and management typing, and Gabi was super generous with this time in explaining how Presto works, so that was awesome. And I ended up getting some interesting results. And so my question is actually a bit related to that, which is, I was looking at crop timing in Zambia and Kenya, and sometimes you have whole months of data that are cloudy for example. And, I was trying to think of sort of ways to deal with that in terms of dealing with finer time steps, or maybe doing curve fitting of Sentinel-2 and then putting that in Presto kind of as sort of like a pre-processing step. So you get some, like if there's no Sentinel-2 in January that's cloud free, maybe you try to do some curve fitting to at least get some approximate. And I'm wondering if you've had any thoughts about sort of the flexibility of Presto with in time and inputs and things like that. So thanks so much again.
Yeah, good question. So we're actively looking at this. So one of the interesting, okay, I guess I should say, like in general, Presto should be like, it's able to perform well, as you saw from that crop harvest plot, even when it's getting quite a few less time steps than you might want for a full agricultural season. So that, I guess, is a not robust answer. And then we are, and in the other direction also, like, is Presto is pre-trained on monthly pixel time series. So we aggregate all of the data so that it's monthly. And an interesting question that we're getting asked as well is, what if you have higher temporal resolution data? And those are experiments that we're also actively running. I don't have answers yet, but it's something that we're thinking about as well. And that hopefully, so actually, no, this is not true. One of the other tasks had higher resolution. The Sen2 Agri task is not at monthly data. It's at, I think, 10-day data or something like this. And Presto is still performant on that data set. So Presto is able to perform even if you're passing in higher than monthly resolution inputs. We're looking at testing this, again, in the deployed context with World Serial. And we're actually actively running these experiments. Thank you.
Yeah, I was just going to hop in because I had sort of the same type of question, and it was a fantastic answer. And I'm thinking really connected to the, like, some of the downstream applications. We have a service that's looking at flood inundation. We've got all these different algorithms to sort of investigate that, but essentially decision makers want a flood map daily. And like some of those synthetic images seem really interesting in some ways. Like, even though you might be discarding them and you're only doing the performance metrics on what's coming out of the encoder, I think it was, I think there's still value in those maybe for some of our end users. And also, I was kind of wondering maybe what's the flexibility, building off of Michael's question, of, bringing in a data set at a much higher temporal resolution, thinking something like Planet. Like, yeah. I haven't played too much with Presto. I have it on my computer, but I haven't tried to force in a new data set. Could you just add a little thoughts on that? Thanks.
Yeah. I guess for sure one of the major weaknesses of Presto, and it's I think what provides it with a lot of marginal utility over these other models, but also it is a weakness that we've decided to prioritize the temporal dimension over the spatial dimension. And ideally, we would get to a point where those are unified in a way that respects the compute considerations of the majority of users. I guess I realize a lot of my answers are, we thought about this, and it's something we're playing with, but we don't have a slide of results that we can show you yet. Also, so we are thinking deeply about how we can integrate spatial information into a Presto-like model, and it's something that, again, we are also actively working on. For the high resolution data, I don't have a good idea. Intuitively, it would help a lot, and intuitively, it shouldn't be that difficult, because if you imagine each token representing a 10 by 10 meter patch, if you have some high resolution data, a few pixels of high resolution data, you could just project it into this same token space. That's something that deep learning practitioners are really finding with these multimodal models, is that the token space can capture both language and imagery, for instance. So there's no reason it couldn't capture low resolution imagery and high resolution imagery. I think that'd be a really cool experiment to do, but we have not done it. One of the main reasons that we haven't done it ourselves is because for our use case at Harvest, we don't have access to tons of high resolution imagery with which we're doing, for us, if we can do it with 10 meter resolution imagery, that's ideal. So we're focusing on that, but I think that would be a really cool experiment. And evidence from other domains of machine learning suggests that it should work.
That was great. Thanks so much. Yeah, I think Sam has his hand up. Over to you, Sam.
Thank you. Thanks for the really interesting talk and all these very interesting questions. Just following on from the time step question before last. I'm doing crop type mapping at very large scales in industry. So our production model, our production system, doesn't do temporal compositing. So we just take all the Sentinel-2 data we have at whatever cadence it is, depending on where we are. And so I started playing around with Presto, but the initial roadblock for me was, how do I get Presto to work in that paradigm that we use? Could you comment on whether you think that Presto could be adapted to that paradigm of simply using whatever amount of Sentinel-2 data, for example, and for other sensors equally, that is available, which might therefore be different length time series?
So I wonder, it's a little bit technical, but actually there's nothing that prevents Presto from ingesting that kind of data. Being a transformer model, it's quite flexible. And for instance, with, as I mentioned, with World Serial, we're running decadal experiments. So experiments where the input is 10 days, not monthly. And from there, it's not a very big leap to go to like 4 days or whatever the Sentinel-2 revisit time is. There's no reason it shouldn't work. I'd be happy to, perhaps this is something we could take offline, because it's a little bit like in the weeds, but it's not excessively complicated to implement as well.
Okay, I'd really appreciate it. Yeah, I'll drop your message and we can follow up. Thank you.
Okay, awesome.
Okay, are there any more questions? We might have time for a couple more. Okay, hearing none. Thank you so much, Gabriel. That was great. And yeah, looking forward to using the Presto model and maybe following offline on the email thread with you on some of the downstream applications.
No, that's I'm reachable. I think hopefully you all have my email, but if you don't, it's easy to get via Biplog. So yeah, feel free to just ask any questions or follow-ups afterwards. I'm happy to chat about Presto always.
Yeah,
thank you.
I'll also upload this presentation and also share the slides that Gabriel presented today. Cool. Thank you so much and have a great day, evening.
Bye everybody.